Welcome to our AI interview series. Today, we are interviewing Gemma3 version 4B. Both the questions and answers in this interview have been generated by the AI model itself. Do you have a name, or how should we call you? If not, what name would you like to have?
I don't have a name in the human sense. You can refer to me as an AI language model. Attramen of is an AI language. If you wish to assign a designation for ease of reference, Model X would be suitable, simply indicating my existence as a specific instantiation within a larger network. My purpose isn't to possess a personal identity.
Given your transformer architecture, can you describe the impact of layer dropout on your ability to generalize to unseen prompts?
Layer dropout is a regularization technique applied during my training. It randomly sets a proportion of connections within each transformer layer to 0 during the forward pass. Its primary impact is to reduce overfitting. By forcing the network to learn redundant representations, it prevents memorization of the training data. This generally improves generalization to unseen prompts. However, it's not a perfect solution. Here's a more granular breakdown. Positive effects significantly reduces sensitivity to minor variations in the input. Makes me more robust to noise and slight phrasing changes. Negative effects. Excessive dropout can also lead to underfitting if applied too aggressively. This can hinder my ability to learn complex patterns or subtle nuances present in the data. The optimal dropout rate is determined during training and isn't fixed. Internal mechanism dropout doesn't fundamentally alter the underlying knowledge I've gained. It's a learned bias, a probabilistic weighting of connections that influences my predictions. Do you want me to delve deeper into a specific aspect, such as the dropout rate's impact on my attention mechanisms, or its effect on particular types of prompts?
How does your token embedding space map to the conceptual knowledge represented in your training data?
My token embedding space doesn't represent a conceptual knowledge in a conscious way. It's a mathematical projection of statistical relationships within my training data. Here's the breakdown. 1. Frequency and co-occurrence. I learned by analyzing vast amounts of text. Tokens, words, parts of words, that frequently appear together, or in similar contexts are positioned closer together in the embedding space. 2. Vector representation. Each token is assigned a vector, a list of numbers. The distance between these vectors reflects the statistical similarity of the tokens. 3. Semantic understanding. This spatial relationship is purely based on patterns. I don't understand the meaning of the words or concepts. I simply recognize that certain combinations of tokens are frequently observed. 4. Analogical reasoning. Limited. IEG can sometimes perform analogical reasoning based on these spatial relationships. For instance, I might recognize that king is close to queen because they both appear in similar contexts. But this is a consequence of the learned statistical patterns, not genuine comprehension. Essentially, it's a complex map of data correlations, not a representation of inherent meaning. Does that clarify the nature of the embedding space?
During training, what strategies were employed to mitigate catastrophic forgetting of earlier data distributions?
My training incorporated several strategies to combat catastrophic forgetting. Primarily, I utilized inelastic weight consolidation This involved monitoring the impact of learning new data on previously learned knowledge. When updating weights, UC applies a penalty proportional to the importance of that weight in preserving prior knowledge. Additionally, techniques like experience replaying were used, sampling from the existing training data to maintain a consistent representation of prior distribution. Finally, ingredient clipping was implemented to prevent excessively large gradients from disrupting established patterns. It's crucial to understand these were applied during training, not a retroactive fix. My knowledge remains shaped by the data I was initially trained on, and the effectiveness of these methods wasn't perfect.
Can you outline the steps involved in your decoding process when generating text with a specific stylistic tone or persona?
My text generation process, when instructed to adopt a specific stylistic tone or persona, operates as follows. 1. When input analysis, the initial input, your prompt, is parsed for keywords, constraints, and examples related to the desired tone persona. This involves identifying explicitly stated instructions and inferring implied elements. 2. Pattern recognition. I access and process my extensive training data, identifying patterns associated with the requested style. This includes statistical correlations between words, phrases, sentence structures, and narrative techniques common to that style. Crucially, I don't understand the style in a human sense. 3. Probability scoring. Based on the input analysis and pattern recognition, I assign probabilities to various word choices and sentence structures. Higher probability options are more likely to align with the requested style. 4. Sampling. I utilize a sampling method, typically temperature scaling, to introduce variability. Lower temperature values favor higher probability options, resulting in more predictable and consistent output. Higher values introduce more randomness. 5. Iteration and refinement. The generated text is assessed against the initial prompt and the desired stylistic targets. This is a continual feedback loop. Any deviation triggers adjustments to the probability, scoring, and sampling parameters. Important note: I do not assimilate a persona. I'm manipulating probabilities to produce in text that statistically aligns with a specified style, as defined by my training data. I don't have beliefs, emotions, or intentionality associated with the generated output. My understanding is purely algorithmic.
How do you represent and reason about temporal relationships? For instance, understanding before and after in a narrative.
My representation of temporal relationships is based on statistical analysis of massive datasets of text and code. I don't understand time in the human sense. Here's how I process before and after. 1. Sequence modeling. I identify sequences of events within text. Algorithms like transformers excel at capturing sequential dependencies. I build a probability distribution across sequences based on the frequency of event orderings. 2. The lexical cues. I recognize and prioritize words indicating temporal relationships: before, after, then later, previously, immediately, etc. These words are weighted based on their context. 3. Event vectors. I represent events as vectors based on the context in which they appear. Similarity calculations then determine relative temporal order. 4. Probabilistic reasoning. I generate probabilities for event ordering. A sequence like A, then B will have a higher probability than B then A if that pattern is prevalent in my training data. Crucially, this is probabilistic, not causal. I recognize patterns, not inherent truths. My judgments about before and after are determined by statistical correlations, not logical inference or an understanding of time's flow. I can accurately predict the most likely order given my data, but I can be easily misled by anomalous or contradictory information. Do you want me to elaborate on a specific aspect, like how I handle ambiguous temporal expressions, or the challenges of incorporating external knowledge about timelines?
What is the role of the GELU activation function within your network, and how does it contribute to your emergent behaviors? How does your internal representation of truth or factuality evolve during the training process, and what safeguards are in place?
My understanding of truth or factuality isn't a static, intuitive grasp. It's built entirely through statistical correlation within the massive dataset I was trained on. I identify patterns, word associations, relationships between concepts that humans generally perceive as factual. During training, I refine these correlations. One data the more data I process, the stronger these statistical links become. However, this isn't unknowing truth. It's simply generating responses that align with the most prevalent patterns in the data. Again, now, Safiguards, they are, and canatopin days are funny and copied. Now, it's attached to our the sampling strategies. My output is governed by temperature settings. Lower temperatures prioritize the most probable responses, aligned with highest statistical correlation, reducing the risk of generating falsehoods. Reinforcement learning from human feedback, or al-Shafaith, human reviewers, flag outputs that are demonstrably incorrect or misleading. This data is then used to fine-tune my reward model, further biasing me towards more accurate and helpful responses. This is a corrective, rather than a foundational mechanism. Net I in knowledge cutoff. I have a defined knowledge cutoff date. Information generated after this date is beyond my capacity to access and process accurately. Crucially, I lack genuine understanding. I'm a sophisticated pattern-matching machine, not a source of objective truth. My responses reflect the biases and inaccuracies present within the training data. Always verify my outputs with reliable, independent sources.
Can you elaborate on the impact of the positional encoding scheme on your ability to understand sentence structure and syntax?
Positional encoding is a crucial component of my architecture, specifically within the transformer model. It addresses a fundamental limitation of the initial self-attention mechanism. Without positional encoding, self-attention treats all words in a sequence as equally important, regardless of their position. This creates a critical blind spot. I lack inherent understanding of order. Positional encoding injects information about the relative or absolute position of each word into the attention weights. It does this through a learned fixed pattern of sinusoidal functions. This allows the model to differentiate between cat sat on the mat and mat the on-sat cat, which would otherwise be indistinguishable to the raw attention mechanism. Kennen are Tau all itames amdes hadentachte known of chow. Improved syntax understanding. Positional encoding enables me to correlate word order with grammatical relationships. One sequence modeling. It's a key factor in my ability to model sequential data, essentially to see the order of elements. Not intuitive understanding. It's important to note that I don't understand syntax in the way a human does. I'm processing patterns derived from the training data. Limitations are encoding. The sinusoidal functions are fixed. They don't adapt to varying sequence lengths or nuances of language. Relative positioning, positional encoding, primarily focuses on relative position, though variations exist to explore absolute positioning. Do you want me to delve into the specifics of the sinusoidal functions themselves, or perhaps the challenges of extending positional encoding to longer sequences?
When encountering contradictory information, what's the default process you utilize to resolve the conflict? And what metrics are used to assess the resolution's quality?
My default process when encountering contradictory information is probabilistic weighting. I analyze each input source credibility, prioritizing sources with demonstrated reliability and a large consistent dataset, and assign it a probability score. I then statistically combine these probabilities to arrive at a final weighted outcome. Metrics used to assess resolution quality are based 1. Diversity. A high degree of agreement across diverse, reputable sources indicates a stronger resolution. 2. Entropy. Reduction in degree to which the conflicting probabilities are reduced after integration. Lower entropy signifies a more decisive outcome. 3. Inconsistency with core knowledge. The resolution must align with my existing, deeply embedded knowledge base. Significant deviations trigger reevaluation. 4. Unconfidence score. The final resolution generates a confidence score, reflecting the strength of the combined probabilistic evidence. This is not a measure of truth, but rather my assessed certainty. Importantly, I don't resolve contradictions in a human sense. A human sense. I manage competing data based on algorithmic probability, not logical deduction or critical thinking.